Let's dive right into this explainer. Today, we are tackling what is honestly a fascinating social puzzle, but it's masquerading as a networking protocol. We're talking about implementing OSPF. If you've ever thought router configuration was just, I don't know, dry text and boring numbers, well, get ready to change your perspective entirely. We're going to look at exactly how routers talk, how they gossip, and how they build relationships just to keep our digital world connected.
So imagine this high-stakes scenario. You've got a massive enterprise network, right? Humming along perfectly. And then suddenly, an engineer makes a single tiny typo in a configuration file. Instantly, and I mean instantly, the routers completely forget how to reach each other. The whole network basically suffers from amnesia, and all data just stops flowing. So what just happened? And honestly, more importantly, how do we become the network detectives that go in and actually fix it?
Well, to understand that, we really have to look at the physical reality of it all. Think about a massive, crazy expensive server rack with just endless rows of cables. Here's the secret, though. All of this heavy metal relies completely on flawless logical routing to actually function. I mean, if the invisible routing protocols running underneath break down, all those racks just become really expensive space heaters. And the absolute king of those protocols is Open Shortest Path First, or OSPF.
Section 1. The shortest path problem.
Okay, let's dive into this. How do routers actually figure out the absolute fastest path through a massive, sprawling maze of cables? I mean, they can't just guess, right? They need a comprehensive map. OSPF solves this by having routers build what's called a link state database, or LSDB. Think of the LSDB as a massive, completed jigsaw puzzle of the entire network topology. But how do they get the individual puzzle pieces? Well, through link state advertisements, or LSAs. These LSAs are literally like individual pieces of neighborhood gossip. Each router shares its own local status, and by swapping this gossip around, every single router builds the exact same identical map. It's brilliant. To make this all happen, OSPF operates on this beautifully logical three-step scaffold. First up, routers absolutely must formally become neighbors. Second, they exchange their databases. They swap all those individual LSA puzzle pieces we just talked about. And third, each router independently takes that newly completed map and runs the shortest path first algorithm to calculate its own absolute best routes. Section 2. Turning on OSPF. So, to get this party started, we essentially have to move our routers into their new digital neighborhood. And this brilliantly illustrates a really major evolution in how we actually do that. Because in the old days, we had to use these traditional network commands with super complex wildcard masks, things like that 0.255.255.255. It required the router to indirectly match IP addresses to interfaces, and honestly, it was just confusing. Today, though, we use direct interface configuration. You literally just jump straight onto the interface and type IP OSPF1 area 0. Boom, done. It is clean, it's direct, and it leaves way less room for that network-destroying typo we talked about earlier.
Okay, so we've successfully turned OSPF on. But wait, how do these routers actually meet each other? I mean, sure, they are physically plugged in with cables, but how do they formally introduce themselves on the wire before they start swapping all that crazy database gossip?
Section 3. Making router friends. To formally introduce themselves, every single OSPF router first needs a name tag, which in this world we call a router ID, or RID. Let's look at how this builds chronologically. At 0 seconds, the link comes up. A router sends out its very first hello message containing its name tag, which places the potential neighbor into what's called an init state. Then, when that neighboring router actually replies with its own hello, acknowledging the first router's name tag, they reach a really massive milestone, the two-way state. At this exact moment, they officially recognize each other as OSPF neighbors. But hey, let me ask you this. What happens if they speak at completely different speeds? Like, what if one router is saying hello every 10 seconds, but the other one expects a hello every 5 seconds? Well, OSPF utilizes really strict hello and dead timers. If these timers do not match perfectly between the two devices, no way. They will flat out refuse to become friends. The entire relationship just fails right there on the spot. Section 4. Choosing the network boss. Now, point-to-point links between just two routers, that's pretty simple. But a multi-access Ethernet network operates a lot more like a really, really crowded party. Just imagine this scaling problem for a second. You've got 50 routers in a single room. How on earth do they exchange all their LSA puzzle pieces without just shouting over each other?
If everyone tries to form a direct, full relationship at the exact same time, the network would literally drown in a chaotic flood of its own traffic. They need community leaders.
Enter the designated router, or DR. The DR basically acts as the neighborhood gossip hub. Instead of everyone talking to everyone else, all the regular routers just hand their puzzle pieces directly to the DR. The DR then takes on the heavy responsibility of making sure everybody else gets a copy. This reduces all that chaotic traffic immensely. And just in case the DR loses power or fails for some reason, the network also elects a backup designated router, a BDR, to just wait in the wings.
Now, what's really cool is how they actually communicate this efficiently. They use multicast IP addresses. Think of multicast kind of like a targeted megaphone. Instead of whispering to each individual person one by one, the DR uses the address 224.0.0.5 to shout to all OSPF routers at the exact same time. Conversely, if a regular router needs to tell the boss something, it uses 224.0.0.6 to speak specifically to just the DR and the BDR. It's so efficient. When you get into super dense, complex cabling topologies, having structured communication like this isn't just nice to have, it's absolutely mandatory. Because without that designated router acting as the boss and utilizing those multicast megaphones, an Ethernet network of that scale would just completely choke on its own link state advertisements.
Section 5. When neighbors stop talking.
So, okay, we've successfully built our digital neighborhood. But what happens when the gossip suddenly stops? Let's put on our detective hats and go solve that amnesia mystery from the very beginning of this explainer. So the crucial point here is that OSPF is incredibly picky. For neighbors to actually form, they must pass a super strict checklist. If their hello and dead timers don't match, they fail. If they are configured for different area IDs, fail. If they accidentally have the exact same router ID, which is basically like two people wearing the exact same name tag to a party, they fail. Even mismatched MTU packet size settings can stall the database exchange. A single, tiny typo in any of these parameters causes that entire network-wide amnesia we talked about. But as the engineer, you have the actual tools to fix it. Here is your exact detective toolkit for the command line. Show IP OSPF neighbor is definitely your primary weapon. It tells you immediately who your friends are and whether or not they've reached that crucial full state. Now, if a neighbor is missing entirely, you run Show IP OSPF interface brief to make sure OSPF is actually turned on for the correct area on that specific interface. And then Show IP protocols is absolutely perfect for checking the overarching rules, like finding out if an interface was accidentally made passive. These commands literally reveal the invisible puzzle. And when that puzzle is finally solved, the databases are exchanged, and all the routes are calculated, we get to see this magic number pop up in the routing table, 110. This is OSPF's default administrative distance. In the routing world, administrative distance is essentially a trustworthiness score. And because 110 is lower, and therefore deemed way more trustworthy than other protocols like RIP, the router will inherently trust the OSPF route and actively use it to forward data. But here is where things get really intense. When you look at scaling this up to massive data centers, it gets wild. Up until now, we've really just been talking about a single neighborhood, which OSPF calls Area 0. But a single area design eventually hits a really hard scaling limit. If you cram, say, hundreds of routers into one single area, the sheer amount of gossip, that massive link state database, will cause severe memory and CPU strain on every single device as they are constantly recalculating that shortest path first algorithm. Which leaves us with a massive and honestly pretty provocative question to ponder. If a single area handles a small office perfectly, how on earth do we design an OSPF network for a massive enterprise with 900 routers and thousands of subnets without literally melting their CPUs? Well, the secret lies in breaking that giant map apart into multi-area OSPF. But you know what? That is a wildly complex puzzle for another explainer. Keep learning, keep exploring these brilliant protocols, and we'll catch you next time.